Let me talk about the potential for a remote day tomorrow. They're going to let us know by 1 o'clock this afternoon what the decision is for tomorrow. Uh, so if tomorrow is a snow day or inclement weather day, uh, I want us to still stay on track with our calendar, but I will push all the homework assignments day, 1 day back. So the homework for tonight will be due on Monday. This will be due on Tuesday. Okay, so everything gets pushed back, but I still want to stay on track with our schedule. So tomorrow, I think should be fairly easy. You guys are really comfortable with power rule for derivatives, and then power rule for integrals is just the opposite procedure. And we're just going to work through pages 16 through 18. Sorry, 29 to 30 in your packets. So we'll do a team session from 10:30 to 11:15. If you can't make it, it's okay. I'll have it recorded. You can watch it at your own time, and we're just going to work through those two pages. And I'll send out a Teams link through Remind around like 5 minutes or 10 minutes before the session starts, and you guys can log in and just work through the pages with me. But the homework will be due on Tuesday, so I'll push everything back in the day. I'm also going to flip-flop the quiz day as well. So the quiz was next Thursday. I'm going to push it to next Friday. But I don't want to lose day of instructions, so I'm going to make 4.3, 4.4 on the 16th. We can still finish up our quiz review, but I do want to start the next topic. Obviously, this section is not going to be on the quiz. I just wanted to buy you an extra day, but then also not lose a day of instruction. Any questions with tomorrow? So today we're talking about extending Riemann sums. What if we're able to add many, many more rectangles? Then our approximations should get better and better and better. Well, then that kind of begs the question, what if we have infinite number of rectangles? Then technically we should be able to arrive at the exact area under a curve. So we're going to be talking about that formula, that definition today. It's a little messy, but it's extending from what we did on Tuesday. So, and I will give you all the formulas that you need on the quiz. You just have to be able to know how to use it. So this is page 9. Yeah, sorry for all the printer marks. That's making the copies a little messy here. Let me just read through here. So we can continually improve the area approximation of a given curve by increasing the number of rectangles. Right. So if you look at 4 rectangles versus 8 rectangles, you can already see that 8 rectangles is going to do a better job of hiding the gaps between the graph and the curve, between the rectangles and the curve. So, if we only had a couple of rectangles, you're going to have larger gaps and more differences. But if we had, 16 or 32 rectangles, our approximation will get better and better because it can more quickly adjust to the ever-changing pattern of the curve. But then if we let the number of rectangles go out to infinity, then it's going to be able to adjust to every change that the curve is undergoing. And so we should be able to arrive at the exact area under the curve. Let me just recap what we did yesterday, because the formula that we're going to see is basically going to to do what we do, but in a more efficient way. Just find a problem that we did before. Okay, so for this one that we did yesterday, we start off by finding the width, right? We found the width. In this case, the width was 1/2. And then we took the 1/2 as the width, and then we started to increment from 0 to 1/2, and we kept adding 1/2 until we reached the end. And each time we found the next interval, we plugged it into the function to find that appropriate height, right? So 1/2 times f of 1/2, that's the width and height. 1/2 plus f of 1, that's the next increment over. And then if I keep adding another 1/2, it'll get us up to 3/2. If I add another 1/2, it'll be up to f of 2. So we're basically going to kind of automate this process through a formula that we're going to see today. All right. So that if we can automate this process, then we can kind of be able to do more than 4, more than 8. We can actually push it out to infinity if we can kind of come up with a formula that can jump to the next term and keep going down this process of adding more and more terms. Okay, so now that you have this big picture in mind, let me share what this formula is doing. So here's the area formula. Again, I'll give you this area formula. You just have to know how to use it, but I do want to kind of explain what's going on here. So just like how the previous example we had width times height, the same thing is going to apply here. The b minus a over n is going to represent the width component of each rectangle. And then the f of a plus b minus a over n times I is going to represent the height component. Now, we are not going to have an n value that we're going to initially, it won't be a constant number at the beginning for us. Because we want to push it out to infinity, we don't want to restrict n to be any number. So we want to leave n as a variable, and then eventually we'll let this n push out to infinity. So b minus a over n, it's just going to be some width, but it's going to have that variable n in it. Before, we will have 1/2 or 1/3 or 1/4. It was a nice constant number, but now it's going to have to stay as a variable because we want that flexibility to push out. Now this one here, f of a plus b minus a over n, this is incrementing to the next value over. So rather than doing by hand f of 1, f of 3/2, f of 2, this is doing the job of incrementing and plugging into the function one by one. So it'll do all that work for us. And then the sigma is going to basically add all the infinite rectangles together. It'll just accumulate all those rectangles together for us. We just have to be able to put into the formula. But we did a smaller version of that yesterday with 4 rectangles, with 5 rectangles. This is what it would look like if we were to push it out to infinite number of rectangles. Okay. All right, so here's example 1. Find the exact area between 4 minus x squared and the x-axis from -2 to 2. So the first things first is we want to build our width. Okay. Our width is b minus a over n. My a value is -2, and my b value is 2. So And then again, we're not going to have a number for n. We're going to leave n as a variable. So b minus a over n will just be what? 2 minus negative 2 over n, which reduces to be what? Just what? What does that clean up to be? 4 over n, right? Okay, so 4 over n. Okay, I'm going to copy down the area formula as I see it above. So limit as n approaches infinity. Let me zoom in a little bit there. B minus a over n, that's our width component. That's 4 over n times f of a plus b minus a over n times I. What's our a value? -2. Now it's inside the function notation, so you're going to do f of -2 plus 4 over n I. So again, this I is going to keep incrementing to the next value over. Before we would do it by hand, right? We start at 0, then we added 1/2, then we plug into the function, then we add another 1/2, plug into the function. So now it's kind of automating that process for us here. But if we want to work this through, we want to involve this function here. Okay. So I want to get this out of function notation, which means I'm going to be taking this entire argument and putting it into the x of the function so that I can multiply and work this through. Because right now in function notation, I can't multiply this out and go any further until I get this out of function notation. So off to the side here, I just want to show you what we're going to do. If f of x is equal to 4 minus x squared, then what we want to do is we want to be able to replace x with the set of parentheses here. So we know that f of -2 plus 4 over ni is equal to 4 minus -2 plus 4 over ni squared. So this is going to replace this. Okay, everybody with me so far? So I'm going to take this and put it into this space here, and then I'm going to multiply the width and the height components together. So we're here at this step now. All right. This is now my height component. And a lot of this is just a bunch of algebra that we have to get through. We have to take the time to FOIL out this -2 plus 4 over ni. So I'm going to -2 plus 4 over ni. I need to FOIL that out. So I'm going to write it out twice. So this will give me 4 minus 8i over n minus 8i over n plus 16 over n squared I squared. So this is what my next step would look like. So little by little, we're going to piece it all together, but this is representing my height component, this is representing my width component, but eventually this is going to turn into what we did on Tuesday, where we got all these terms combined like terms. We're going to separate into individual summation rules and then find the limit. Okay. Give you guys a moment to catch up. So now I'm just trying to figure out how I can get this, what's inside the bracket to clean up a little bit more. I'm going to combine these like terms there. -8 minus 8 is -16. Sorry, I skipped a step here. And then what I did next, after I combined these like terms, was I distributed the negative through, so I can get rid of the parentheses and I can start combining the like terms. So 4 minus 4 plus 16 over ni minus 16 over n squared I squared. The 4's canceled out, and then I can now look at that width component outside of my bracket and distribute that through, and then I should be able to get rid of all my brackets and parentheses. So next step, I'm going to distribute that 4 over n through. And once I distribute it through, then my next step is see if I can involve a summation for each of those. And as I do that, I'm going to involve a summation for each of those terms. But we talked about Tuesday how we're able to kind of isolate the parts that we want to use for the rule. So the 64 and n squared or 64 and n cubed will just get pushed down in front because we know these are just going to be coefficients. And the rule that's going to impact us is going to be summation I and summation I squared. Now this should feel more familiar because this is from this point on is what we were doing on Tuesday. Any questions so far? Okay, so if we think about the rule for summation I, was n times n plus 1 divided by 2. And then the rule for summation I squared is n times n plus 1 times 2n plus 1 all over 6. And I'll give those to you. You don't have to memorize them. Okay, so from here, we have two separate fractions. We just have to figure out the degrees that match so that we can pull the coefficients. And same thing here as well. Now, this one we talked about before, how we can save a little bit of time, right? We don't have to boil out the entire thing, just the most important parts, the first thing of each term, because we only care about the highest degree. Anything that's lower than higher degree is not going to impact my limit. So 64n times 2n will give me 128. I'm going to say plus dot 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 because we're going to have lower degree terms, but it's not going to matter because we only care about the highest degree, right? So what's going to come out of this first fraction? Just 32, right? 64 over 2, which is 32. And then the next one is 128 over 6. Enter that in our calculator, we'll get 32 over 3. So what does this number tell us? This number tells us that after adding infinite number of rectangles, we're able to not only achieve an approximation, it is actually the exact area under the curve, because we're not just doing a lower sum or upper sum, or we're still adding rectangles, but we're pushing it out to infinite number of rectangles. So this is the exact area of the curved region. So the graph may look something like this. And we're essentially finding the exact area of this region, which is 32 over 3. Okay, let's see if we can do at least one more, and if possible, let's do two more. So this is page 11. I put it on the half sheet, so we'll try number 1 and 2. And the key is attached on page 12. So let's see if we can practice through this process. So first things first, you want to go ahead and find your width, find your b minus a over n. Again, your n is going to stay as an n. Your n is not going to turn into a number. We want to have that flexibility to change that n, push it out to infinity. So, all right, go ahead and try your steps, and I will follow up one step by each step by step once you guys had a chance to kind of give it a shot. So first thing is just trying to get this definition off the ground. After that, your next step is trying to get this out of function notation. I can't multiply these together because these are not compatible. I have to get this out of function notation. The way you do it is you take this argument and you insert it into the x of the function, and then that is going to be the expression that you're going to put in place of that. So all the x's are going to get replaced with that messy argument that you see there. So I highlighted in green what you're going to put into the function, and that is going to now represent what we're going to be working with. Everybody good getting from here to here? Because after this, it's just a bunch of algebra. Okay, so now we have everything in front of us. Now we can just focus on algebraically, how can I clean up my parentheses, clean up my brackets, combine my terms, and get everything all cleaned up with all the brackets and parentheses eventually removed. So careful with the parentheses squared that you're just not distributing the exponents through. We got to take the time to FOIL out, write out your parentheses out twice, FOIL out each term, then distribute the two through. There's just a bunch of messy algebra here. So we're still inside the bracket. We're still working on that height component. We haven't touched the width yet. We'll save that width 2 over n until we get everything inside the bracket all as cleaned up as we can get it. Okay, next step. After this, I'll just distribute the 2 through the parentheses, distribute the 3 through the parentheses, combine my terms, and then I can worry about finishing that 2 over n out in front. So at this stage, now all the brackets and parentheses, everything is resolved. Now I can look at, okay, I have 3 terms there. I'm going to start separating into summation rules and then pushing out coefficients. And I should be able to just rely on my summation I squared, summation I, and summation 1 rule. And once everything's in terms of n, then you look at your limit as n approaches infinity. Each fraction will have a matching set of degrees, and you're just pulling the appropriate coefficients from each fraction. The summation I squared feels messy. You have to pull all that out. So our shortcut is just multiply the first thing in each part, and that will get you your highest degree along with the coefficient. And the rest we can ignore because lower degrees is not going to impact that first fraction except what's n cubed. So I get 32n cubed over 6n cubed. The second fraction, I get 4n squared over 2n squared. And last fraction, I get 2n over n. All these within each fraction has a set of matching degrees. My degree 3 here, highest degree is degree 3, so 32 over 6 is all I need from that. Degree 2 here are matching, so whole out is 4 over 2, which is 2. And then the 2n over n is just 2. Add that up. The exact area under this curve between my bounds is 28 over 3. Any questions? All right, let's see if we can do one more, and this will be the last thing that we do today. So number 2, same process. Follow the definition. Your b minus a over n will give you 5 over n. F of -1 plus 5 over ni. Keep in mind that you're always going to be starting off with function notation, and you have to always get that piece out of function notation. You have to plug it back to the original function. So I highlighted what needs to happen. You have to get that -1 plus 5 over ni into the x's of the original function. And then once you've made that substitution, then it's just a bunch of algebra. Can we clean this up? FOIL, expand, combine like terms, right? So actually what we found here is actually displacement. It's not quite area, because we have more parts of the graph that sits below the x-axis. So that's why we're getting that negative number. But usually area is a positive number. So eventually we're going to have a specific formula for area that will always ensure it's a positive number. But for now, we're going to have areas in quotes, like it's area related, but it's not quite area. We'll talk about that distinction a little bit later, but that's why we're getting a negative number. We have more parts of the graph, a large portion of the graph below the x-axis, so it's accumulating all these negative y values. So that's why we're getting these negative numbers. Okay. Any questions? We can skip the 4.6, the trapezoid rule. I'll do that probably, if not tomorrow, then I'll do it on Monday. But I just want to give a quick preview into tomorrow, just so that kind of have it in case we're doing the lesson online. Let's say I had a function that was 3x to the fourth. What's the derivative? 12x cubed. Right? Think about the operation that you did, right? You did multiply. And then you subtracted 1, right? So this semester is all about getting back to where we came from. So if I want to get from 12x cubed back to 3x to the fourth, instead of multiply and subtract, we're going to do what? Divide and add, right? So this is the process we're going to talk about tomorrow. If I want to take this is the notation for antiderivative. If I want to take the antiderivative, instead of subtracting, I'm going to add 1. So it's going to be 12x to the fourth. And instead of multiplying, I'm going to divide. So it's going to be divided by 4. And that's going to take me back up to 3x. But that's what we're doing tomorrow. Yeah, but that's the big picture for tomorrow. So again, tomorrow, if you look on the board there, if you came in late, if we have a remote day tomorrow, we'll be working on pages 29 to 30. The team session will be 10:30 for the team. I'll send out a Teams link to you through Remind about 5 minutes before, and then you can join in and work through those 2 pages with me. That would be great. If you can't make it for some reason, I'll record it. You can watch it another time. But I'm also pushing, if tomorrow's a remote day, I'll push all the homework days back 1 day. So on Monday, I'll be checking tonight's homework, and then on Tuesday, I'll be checking Friday's. All right, go get your phone. Okay, great. Thank you. Yes, yeah. Thanks.
Well, I have it.
Really? Thank you.
Has to be group of one. There's other groups.
Oh.
Great, thanks.
Well, I mean, we can take that one.
Oh, really?
All that stuff.
Which that's something that's sitting, like. That's it. No, tell me, and I just make it. I only got 2 weeks.